Okay, today we are going to talk about digital epidemiology statistics. Today is lecture number 3. I just remind that lecture number 1, we discussed the possibility of using web services, which is application programming interfaces, and we also discuss how this can give a tremendous uplift to the whole public health in this country. It can create a revolution actually in public health. Second lecture, we spoke about data sources, and this is very important because in public health we have many sources. We have sources that are related to public health organizations and not public health organizations, such as, for example, environmental data, social determinant of health, and many other things. Lecture 3, we will talk about the digital epidemiology. And also, we will start with introduction to statistics because we are going to use it in lecture number 4. Okay, so let me just share my screen. Okay, so I share my screen now. And we will talk first about digital health in general, then digital epidemiology, and then introduction to statistics. All right, so what does it mean actually digital health? So digital health, it's a wide range discipline that includes mobile health applications, health information technology, healthcare information technology, public health information technology, informatics and technology. Then we have wearable devices, we have telehealth, telemedicine, and personalized medicine based on genome. So everything this goes under umbrella of digital health because we use different algorithms that processes data, and digital health actually works with numerical data. So therefore it is digital health. Now we have a definition of epidemiology, and epidemiology is a branch of medical science that investigates all the factors that determine the presence or absence of diseases or disorders. So epidemiological research helps understand how many people have a disease or disorder if those numbers are changing. So this is important. And epidemiology, we have, it can be passive and active. And for example, passive, it always monitors changes in various parameters like disease and disorders, number of population, the severity, and so forth. And how many public health disorders affect our society and our economy. So it is a very, very wide discipline, epidemiology. Now, when one of the tools of epidemiological surveys is just when used, for example, telephone, you send questionnaires and so forth, but answers that people provide are not, can be digital, that can be categorical. For instance, numerical categorical. For example, some people answer, I don't remember, not so well, I don't know, I'm not sure, and so forth, and give some remarks, some things in a categorical way. So it is not in terms of numbers. And therefore, epidemiological surveys are also quite a broad discipline. And out of this discipline, we talk about digital epidemiology. And digital epidemiology is a new field, a relatively new field, that has been growing very rapidly in the past few years, fueled by the increasing availability of data and computing power. You know that data coming every year in the exponential order. So it is like a exponential function. So lots of data coming, and as well as by breakthrough public health analytics methods. So the public health analytics methods increase together with exponential increase of data that we have in health care. Now, digital epidemiology is epidemiology leveraging numerical data. This is very important. So this information is given in numerical data, in digits. So this is digital epidemiology, it's called. So it is the same objective of digital epidemiology and the same as objective of conventional epidemiology. All right, so what does it mean, syndromic surveillance? Syndromic surveillance is a population-based early detection and monitoring system. So this is also a very, very useful, very important discipline in public health, because we call it early detection information system. In my future lectures, I will talk about information systems, and syndromic surveillance is one. And what is good, it works in real time, because not all information systems in public health work in real time. And this is quite important. It uses data collected in real time from emergency department, for example, and other clinical and non-clinical sources. So syndromic surveillance networks are based on reports of clinical symptoms from hospitals and selected primary and secondary healthcare facilities, which agree to provide regular surveillance data of all cases. So syndromic surveillance works with not only, but works tightly with the emergency department. It also gets data from other sources, including, for instance, social media. And about social media, we will also talk in a lecture that devoted to these kind of surveys. Now, syndromic surveillance provides public health officials with a digital platform to detect, characterize, monitor, and respond to public health threats. More accurate public health decisions also coming from syndromic surveillance. Syndromic surveillance also provides awareness about public health concerns, and it contributes to protecting the health of communities. So that is the activities of syndromic surveillance. Okay, and the syndromic surveillance, as you remember from lecture number 2, is also comprises one of the data sources that we use in public health. Now, syndromic surveillance is a collaborative effort between local and state health departments, CDC, and other partners. So suppose now John Doe doesn't feel well, so he has some symptoms of flu or something, and he has a high fever, headache, sore throat, and he wants to go to the emergency room, ER, emergency department of a hospital for urgent care. So what happens with in terms of data that we collect on John Doe? In the emergency room, he goes there and he has different exams. For example, healthcare provider in the emergency room can ask for lab test or maybe X-ray or something, and all kind of data that we receive from John Doe in the emergency room. The emergency room sends the de-identified data, including chief complaint, diagnosis codes, patient characteristics to state and local health department. Okay, so all this data go to state and local health department, but also John Doe's data, it can be including his name, it goes to the data aggregator such as health information exchanges. So why it is important? Because, for example, in the next time, if John Doe goes to emergency room and if he is not able to give exactly, for example, what these complaints are, chief complaints, maybe he's unconscious and so forth. So this hospital goes to HIE in terms of data. He collects all information about John Doe from these data aggregators. Okay. Now, what I want to tell you that public health department and health information exchanges can contribute data to the NSSP, and we spoke about this in lecture number 2. It is NSSP. It is the National Syndrome Surveillance Program that have sometimes they get millions of patient data sets a day. So it is a huge repository and a digital platform, which is called NSSP Biosense platform. So all this data that come from patients who go to ER or just to healthcare facilities, they go to NSSP Biosense platform in terms of electronic records. Okay, now digital data are created by the public both at the population level and at the individual level for epidemiological assessment and public health intervention, and with the support of clinical case management. They are also informed by conventional surveillance via laboratory and clinical notification. This feeds into public health decision-making and communication with the public through digital channels. Other relevant sources of information include demographic, economic, social, transport, weather, and environmental data. And I would like to mention here that actually lots of activities in public health informatics and technology, they're focusing that on finally feed the data to decision support system. It can be on the level of the patient. It can be at the level of communities. For instance, when we talk about different emergencies, pandemics, and so forth. So that is the decision support system, very important, and we will talk about it in a special lecture, and we actually will build a system that makes this decision based on different data sets. Okay. Now, the World Health Organization, which is abbreviation WHO, WHO platform, EPI Brain, also offers different data sets for infectious disease emergency preparedness and response, including environmental and meteorological data. And we were going to use some of the data sets from this platform. It's quite handy. Now, public health informatics and technology has long been underfunded compared with the funding of other areas of health. It constitutes actually a few percent of the total funding. So it's not funded the way that it should be. The long-term changes may necessitate investment in national centers of excellence. And we assume that the US government will build such national centers of excellence. It will be a great idea because national centers of excellence can work for a long time. Okay, this is important. A substantial investment in workforce education and skills is essential for growing public health informatics and technology leadership of the United States. So why workforce is so critical? Because, as I said, that data, volumes of data coming in exponential proportions, very, very fast and in large volumes, and we call this big data. And we do not have enough people who could work on a daily basis that are professional working with these great volumes. Okay, we have this necessity now, and in the future, this necessity will be even more critical. Now, what happens is COVID-19 showed that digital technologies offer tools for supporting a pandemic response. The digital technologies have an important role in comprehensive response to outbreaks and pandemics, complementing conventional public health measures and thereby contributing to reducing the human and economic impact of COVID-19. So we learned lots of things from COVID-19 that was not visible before. COVID-19 also showed that the future of public health will be increasingly digital. Digital public health will play a major role in future challenges, including pandemic preparedness planning. So key stakeholders in the digital field, such as technology company, public health-oriented organization, even schools of public health universities, should be long-term partners in preparedness rather than being partners only when emergencies are ongoing. So therefore, the development of centers of excellence can be critical, and it is in acute need in this country. Okay, now let's talk about some statistics. So first of all, we will talk about descriptive statistics, and descriptive statistics, we know it is just a general information, statistical information we get from data. we have also inferential statistics. Inferential statistics is the idea is to analyze samples and based on these samples to give some conjectures to some give some evaluation of population. And in lecture 4, we will talk about it, how we can estimate, for example, the proportion of females and males living in the state of Maryland. So descriptive statistics is the following. We take different, we have, let's say, data, we sum them and divide by the number of population. So this is a population mean, okay? Now, if, for example, I have a population with just 1, 3, 4, some characteristic, 0, -1. So the mean value will be, you have to sum up all these numbers, the x, divided by the number of elements, which is 1, 2, 3, 4, 5, 5. So 5, and have 1 plus 3 plus 4 plus 0 minus 1. So what I will have, I have 7 over 5. 7 over 5, which is 1 and 2 over 5, or 1.4. Okay, so this is how we calculate the mean. Now we have in Python this program, and I told you at the beginning that we will also devote a few lectures for Python, and I will just explain you how many problems can be solved using Python code. But I don't want to say that Python code is the only one that we can use. There is different codes like programming codes like R and SAS and so forth, but Python code is not only a language, it's also optimizer. It optimizes computation. Therefore, in public health, when you have many data, we use lots of Python code. So if it is simple, that in a few lines, you can do average of any kind of data sets. For example, this one. Okay, now, what is the median? Median is a number which is in between, in the middle. For example, these numbers is, suppose I have this sequence, I have to put them in order, in ascending order. So starting from -2 goes to 100.2, goes to ascending order. And it is clear that the middle point is 3. So median is the left, and 1, 2, 3, 4 points to the right. Okay, so it is very simple. When we have even numbers, we have also to put them in ascending order, and in here we have we should take 2 points in the middle and divide by 2 to make average. In this case, it will be 2.55 if we have even numbers. So even numbers and odd numbers. Okay, now this is a Python code for finding median. You can take any kind of data and you will get very fast calculated median. But why median is so important? So before going to that, I will tell you also that in descriptive statistics, also another one parameter which is called mode. So we have mean, we have median, we have mode. Mode is in public health, we do not use much, as I told you. So because it's not representative. But what we use mode when we have tables, we have data sets. For example, we can say that in feature F1 feature, okay, we have mode, will be 17 because it is 2 times is 17 represents twice in its feature. And for example, F4, we have mode 1, 0, 0, 1. It is here, it is 3 times. It is more than anything else, more times. So it is 3 times here. So mode in F4, it is mode in F4 will be 1, 0, 0, 1. So 1001. Okay, now the median we use a lot in public health, median. Okay, and of course mean, because other statistical parameters such as variance and standard deviation, they use mean, right? But the medium divides data set in called quartiles. Something like this. I'll just make it a little bit better. Okay, so it's something like that. So this is data, and this is quartiles. So we have these 4 segments, 1, 2, 1, 2, 3, and we have the quartiles Q1, Q2, Q3, and here is, and here is, that's it. Okay, but I will just put here some more data here, so to give, so you see that we have data also to the right. So we have data here from the smallest number to Q1. Then we have data between Q1 and Q2, from Q2 to Q3, and from Q3, we have to the maximum, to the largest number. Let me just put you a little bit better. Okay, Q1, 2, Q1, 3. Okay, so it is clear from this picture that Q2 divides is a median for all data set. For the whole data set, Q2 is a median, right? And get Q1 divides, it is very simple, divides this segment from Q2 to the smallest number by 2, and this will be Q1. And the Q3 divides the segment from Q2 to the large number. So it will be Q3. I also like to put here it is small number, Sn. This is a large number, Ln. And so we have 1, 2, 3, 4. And therefore it's called quartile. So quartile is coming from this. We have small number to the smallest number to Q1, from Q1 to Q2, from Q2 to Q3, from Q3 to large number. Okay, that is how it works. So in this picture, we have the same thing. We have a very few numbers here, but we have, this is 1 quartile, this is 2nd quartile, this is 3rd quartile, and this is 4th quartile. And this we have Q1, Q2, and Q3. Now, these Q2 and Q3 are quite important, and we need to calculate them. Okay, so for this, we have a very simple Python code. And if we put in this Python code any sequence, it gives you right away Q1. Q1, in this case, it is 6. Q2, in this case, it is 45.5. And Q3, Q2, Q3, it is 63.5. So this is just 2 lines, and you can calculate any even very large data set. You can have quartiles. Okay, now, suppose you have a hospital. Suppose you have a hospital, and each hospital, H1 and H2, they conduct MRI tests. Now, here is 10 days, and the first hospital in the first day has 5 MRIs, then 7, then 3, 6, 9, 11, 20, 12, 23. A second hospital conducts MRI test 1, 3, 2, 7, 4, 9, 10, 11, 12. Let's see what happens here. So we will first use this Python program. And instead of this sequence, we put sequence H1 and sequence H2. And we calculate right away quartiles. It will be Q1 5.5. The second will be Q2 is 9, and Q3 will be 16. Okay? So the whole data set will be distributed from small number Sn I put here. It will be to Q1. Then I have Q2. Then I have Q3. And I have a large number. So I have 4 quartiles here. Now, what happens here? We have a very important parameter when we talk about quartiles, which is called IQR. IQR is interquartile range, and this is here. So interquartile range has 50% of all the data. Okay. Now, what happens? We will do now a very important thing. First of all, it is very nice, and data visualization also is one of the most important elements that we train our students in. One of these elements important in visualization, it is box plot. Box plot gives you the smallest number, Sn, then gives you median, this is Q2, Q2. This is Q1, this is Q3, and this is large number, the largest number. Okay, so same thing is here. So we see here that in this case of the first hospital, we have data more concentrated. So it is the number of MRIs made in this hospital. They are more spread from smallest number to largest number. So not much concentrated. But in the second hospital, we have very high concentration. So the number of, so at least 50% number of MRIs in second hospital is here. So it is quite concentrated. Okay, but this is not what I would like to say you. I would like to tell you one thing, that this can be used to eliminate outliers. And outliers cause us lots of difficulties when we process public health data. Why? Because public health data, not only public health data, but also data coming from other sources, we call them raw data, and they are sometimes dirty. So they have, for example, some mistakes, some errors, some blanks, and many other things. Okay, and without it, we can make very erratic solutions and results if we do not make the data of better quality. And one of the steps to make that data of better quality is eliminate outliers. So in this case, for example, we have 5, 7, 3, 6, 9, 11, and here is 2000. It is clear that there is no 2000 MRIs. So it was a mistake. Maybe it was a receptionist who made a mistake. Instead of 20, they put 2000. Okay, but it happens all the time. So outliers cause lots of problems. And I will just tell you how we can get rid of them. In this case, it was even worse. It shows that one day, the hospital number 1 conducted negative 40 MRIs, which is also, of course, a mistake. Somebody put minus here. Maybe this 40 also is not correct. So that was a mistake. It's like glaring evident mistake. So we need to eliminate this and we need to eliminate that. But imagine that we have millions of entries. Okay, that is impossible for a person to go from this to that and to compare and everything. So we use a box plot. And this is a very simple Python code, gives you, makes you a box plot. So we have this, again, 2000 and negative 40. And what we have now, we have box plot now becomes this one. So actually, it is true that we need, it is a rule. It's not only theoretical, but it's practical rule. So we just eliminate outliers that exceed 2 times IQR. So that is when 50% data located. So everything twice that can be suspicious for outliers. So what does it mean? I go back to this. So we have to put here, for example, this and this will be somewhere here. So everything what exceeds this distance, twice that, and also here twice that, you can suspect for outlier. Okay, so now things here is, of course, way, because this is the IQR is so small, so tiny, and this outlier is so far. So this is, of course, outlier, and we need to eliminate. When you eliminate this, you will get this something like that, these plots, which are regular, which are acceptable. Let's see what happens with the second hospital. Second hospital is this one. It's a little bit better because in the first, you see this outlier cost, this becomes very tiny, like a thread. And here is like that. So this also outliers because it is twice that, IQR twice, and everything here can be suspected for outliers, and here is way below. So we have to eliminate this negative 40. We have to eliminate this one, and you will get perfect data quality, so that you can make decision. Now, finally, I would like to tell you what does mean variance and standard deviation. Variance is if, for example, you have mean value, for example, 2, and I have data like this. Okay, so variance will be this, for example, 1, this is negative 1, this is again 1, this is 1.5, and this is negative 2. So your variance will be, this is mean value equals mu. So variance will be from this formula, will be 1 minus 1 minus 2 squared. Here, plus 1 minus 2 again, squared. plus this one will be minus -1, negative -2 squared, and so forth. And this gives you variance. Square root of variance, it is called standard deviation. You can see it from this formula. Square root of variance is standard deviation. But we'll talk about population, the whole population. But when you take sample of this population, the only thing what changes, it changes that instead of the whole number, you divide, let's say, variance. In this case will be, for example, how many points I have? 1, 2, 3, 4, 5. You have to divide standard deviation, this one, by n-1. Okay, this is important, and I will explain to you why we have this notation. So we have to divide samples not by n, by n-1, and also variance we have divided by n-1, and I will explain to you why it is when we will talk about how we make surveys. Okay, so this is a convention. So we divided samples by not by n, but n-1, and the Python code for this, I guess, will be, I will show you. So this is a variance formula for population. This is variance formula for sample. You see it's n-1. And this is the code, Python code for standard deviation population and for sample. It is very simple, and you can calculate variance and for population, variance for sample, and you can do at home. You can take any kind of, for example, data set and put this instead of this data set, you put your data set, and you can see your variance in for, let's say, for variance and for a sample. Okay, so you take a sample and you take a variance. For example, you have 1, 2, 3, 0, 5, 6. This will be your population. So you can use this formula for population. And 1, 2, 3, it is sample. And you use formula for sample, just divide by n-1. And you calculate variance and standard deviation. All right, so for today we finish. And lecture 4 is devoted to better understanding of how we do surveys, central limit theorem, a law of large numbers, and hypothesis testing. Okay, bye-bye.